All right. So this is going to be our fifth week for the engineering economics class, and now is the time to change the cash flow periods in our study, and we are just going to study this under the discrete periodic compounding. So what is the main story of discrete periodic compounding? We have stated previously that not every engineering economics problem, not in every engineering economics problem, the cash flows are made on annual basis. We usually observe in real life, we usually observe that the cash flows occurring periodically in different time units, such as monthly payments or weekly payments or quarterly payments. So in that case, how are we going to make our engineering economics analysis will be taught in this chapter. And in the second part of this chapter, we are going to study the geometric series of cash flows, which is actually a new type of series. And we are going to study in the second part of this week's lecture. So the outline is as follows. First, we are going to mention about discrete periodic compounding, and in order to study different periods of cash flows, we need to understand the difference between the nominal and the effective interest rates. Okay, so from now on, we are going to define the nominal interest rate for the annual compounding interest rates, but the effective interest rate is going to be defined for the periods. We are going to understand this difference, then we are going to solve three different types of problems. Now, the distinction between the nominal and the effective interest rates is realized when the interest periods are not coinciding with the payment periods. So what is an interest period? What's the payment period? Let's just say the payments are made on a monthly basis, which means in the end of every month, you are making payments. However, the interest that your account is being subject to is not compounding on a monthly basis. So the interest compounding periods can be different than the payment periods. Now, first, we are going to focus on the simple, and we will study the problems when the interest periods are coinciding with the payment periods. Then we are going to study the problems when the interest periods are smaller than the payment periods, which means the compounding occurs more than once between two consecutive payments. So let's just say you are making payments on a quarterly basis in the end of every 3 months. However, the interest in the account is compounding on a monthly basis. So in that case, the interest periods are smaller than the payment periods. And there's also the opposite problem where the interest periods are larger than the payment periods, which means in your account, the interest compounds on a quarterly basis, or let's just say yearly basis. However, you are making payments in the end of every month. So the payment periods are this time smaller than the interest periods. So we are going to study each of these three types of problems. And we are going to continue with the second phase, where we are going to learn about the geometric series of cash flows, which requires a little theoretical calculation, but in the end, the problems related to geometric series of cash flows are also very easy. Now, first of all, we need to define the difference between the nominal and the effective interest rate. Now, you see, many financial transactions require that interest be compounded more often than once a year. For example, if you take a loan from a bank, you are going to be exposed to a interest which compounds on a monthly basis. So the compounding, interest compounding, will occur in the end of every month. So which means in the next month, you are also going to be paying the interest of the interest that is compounded in the previous month. So the compounding will apply 12 times a year, actually. Now, There are also other types of transactions which will be exposed to quarterly compounding interests, which means the compounding occurs in the end of every 3 months, or daily compounding may apply, which means on every day the compounding will occur, etc. Now, because of that reason, because the compounding may be different, the compounding periods may be different than the pay periods or the cash flow periods, we are going to define 2 new interest rates. So to understand the distinction between the effective interest rate and the annual interest rate, the first term is called the nominal interest rate, which is the annual rate that is quoted when describing an interest-bearing transaction. So if you are going to have a savings account, or if you want to take a loan from the bank, over the contract, the interest rate that is going to be written will be an annual interest rate, which is denoted with lowercase r, and that annual rate is the interest rate that corresponds to a year. Okay, but the nominal interest rate is not going to be the interest rate that we are going to use in our formulations. So we need to compute the effective interest rate. Now, this is the annual rate. However, the nominal interest rate is the annual interest rate. However, if the compounding occurs in different periods, okay, different periods, we call these interest periods. Compounding periods are called interest periods. If the interest periods are different than years, then we need to compute the effective interest rate that corresponds to the actual interest period or the compounding cycle. Okay, for example, so how do we do that? How do we calculate the effective interest rate from the nominal interest rate? It is not very hard, actually. It is very easy. So in order to know that, we need to count how many compounding periods that occur in a year. For example, if the interest compounds on a monthly basis, this means in a year, there will be 12 compounding. So here, the letter m, lowercase m, represents the number of compounding cycles in a year. If we have an account in which the interest compounds on monthly basis, in that case, the number of compound periods per year will be 12. M is going to be equal to 12. If we have a daily compounding account, then the number of compounding cycles in a year will be 365. And if we have a quarterly compounding account, in that case, the number of compounding cycles within a year will be 4, because there are 4 quarters in a year. Now, how we are calculating the effective interest rate that corresponds to a compounding cycle from the nominal interest rate? It is simple. We are just dividing the nominal interest rate to the number of compound periods in a year. So we calculate the effective interest that corresponds to our period. All right, so in this first question, we are going to understand the distinction between a nominal and the effective interest. Now, a bank claims to pay interest to its depositors at the rate of 6% per year, but compounded quarterly. So you see, in this sentence, the interest rate is defined for yearly periods. This means this interest rate, 6%, is the nominal interest rate. However, the compounding occurs in a different period than years. So compounding occurs quarterly. This means there is an effective interest rate that is defined for each quarter. So the question is this: what are the nominal and the effective interest rates? What is the annual compound amount factor? First of all, the nominal interest rate is 6%, which is written on the contract. So this is the annual interest rate which is claimed by the bank. Now, the nominal interest rate is not something that is realized. It is just a value which summarizes the annual nominal interest rate. Okay, so it is just a value which is written on the contract. The effective interest rate per quarter, for each quarter, the effective interest rate will be 1.5%, which means we are going to divide the nominal interest rate to 4 because there are 4 quarters in a year. So the effective interest rate applied in each quarter is 1.5%. Now, what is the annual compound amount factor? Or in other words, if you invest $1 or if you deposit $1 to this bank, in the end of the year, what would its new value be? Okay, so what happens to your $1? So this is going to be called the annual compound amount factor. Now you see, your $1 is going to be exposed to 4 compounding interest per year in each quarter at a rate of 1.5%. Therefore, there will be 4 times compounding for your $1, and the yearly compounding factor will be 1 plus I to the power m, where I is the interest rate for each quarter and m is the number of quarters in a year. So your $1 will become 1.0614. So 1.0614 is what it is, basically the annual compound amount. And it is also called, so this 6.14%, 6.14% is called the effective interest rate per year. So 1.5% is the effective interest rate per quarter, and 6.14 is the effective interest rate per year, where 6% is the nominal interest rate. Okay, so actually, if you keep your money in this bank account for 1 year, the actual effective interest that you are going to get is a little larger than the nominal interest rate. So this is 6.14 actually. However, as we have said, the nominal interest rate is the simplest interest term that is written on the contracts. Now you need to read between the lines. Though the nominal interest rate is defined, it is also stated in the contract that the compounding occurs on quarterly basis. All right, so let's solve another question to understand the nominal and the effective interest rate for the following problems that we are going to solve. It says if you invest $10 in a savings account that pays interest at a rate of 10% per year, but compounded monthly, what accumulates in the account in 5 years? All right, so how are we going to solve this problem? First of all, we are going to invest or deposit a principal of $10. Okay, now the account that we deposit this money is paying us a 10% annual interest. However, the compounding occurs in different periods than years. So we need to understand at this point that this 10% per year is the nominal interest rate, which is not actually realized. So it is just defining the interest, nominal interest rate here. However, the compounding occurs on monthly basis. So we need to determine the effective interest per month. And in the end of the question, it is asking how much money accumulates in the account in the end of the 5th year, in 5 years. Now, in this problem, we need to be careful. So the future value will be calculated in the end of the 5th year. The future value will be calculated by multiplying our principal of $10 with the single payment compound amount factor, right? Now, first of all, the effective interest rate is calculated as R over M for each month. And for how many months we have compounding occurring in 5 years? Actually, there are 12 times 5 different months in a year, in 5 years, okay? So 12 times 5 is 60. Actually, in this problem, the $10 is going to be exposed to 60 compoundings, and in each compounding, the effective interest rate will be 0.10 divided by 12. So we calculate the effective interest rate for each period, and we also calculate the number of periods in our problem. So from now on, we are not going to study all problems in yearly basis. Sometimes the payments and compounding may occur in different periods. So in that case, we focus on the compounding period just like here. And in each compounding period, we calculate the effective interest rate. Right now, it is R over M. And we also calculate how many compounding periods do we have in the total investment horizon of 5 years. In this case, we have 12 times 5, 60 compounding periods. So $10 will be compounded by the compound amount factor, which is calculated for the effective interest rate for each period and number of interest periods in 5 years. Now your $10 becomes 16.45 using this formula. Or you can use an approximation from the compound interest table as well. Remember now, the future value is equal to the principal times the single payment compound amount factor. However, you need to be very careful. At this point, we have 60 periods of compounding, and in each compounding period, the effective interest rate is 0.10 divided by 12, or in percentage, 0.833%. Now, the problem is what here? Of course, we do not, if we want to search for this single payment compound amount factor from the interest tables, we do not have a page that corresponds to such an interest rate. Therefore, we either use an approximation, linear approximation between two values, or we can use the formula as above here. We can use the direct formula to calculate this future value, and we are going to get something very close to $16.45. Now, as we have said in the beginning of the lecture, we are going to study 3 different types of problems, and in the first type of problem, we will assume that the interest periods are coinciding with the payment periods. Actually, in the previous 2 questions that we have solved so far, this was just the case. So you see, we have a single payment in the beginning, and we are looking for the future value in the end. So we are not making any payments throughout the investment horizon. So in these problems, if we are solving any problem with a single payment in the beginning and in the end, in that case, the type of problems that we are solving are falling into this class. However, of course, there will be uniform series of payments in these kind of problems as well. So we need to give an example about them at this point. Okay, so when the interest periods and the payment periods coincide, we first compute the effective interest rate and directly use the compound interest formulas or the compound interest tables. So if we have the payment periods and the interest periods same, for example, you have a problem where you are making monthly payments and also the compounding occurs monthly. In that case, the solution is very simple. First, you need to calculate the effective interest rate in your compounding periods, which is calculated by dividing the nominal interest rate to the number of compounding periods in a year. And then, instead of using the number of years in the investment horizon, you need to calculate the number of interest periods in your investment horizon, which is number of years n times the number of compounding periods in each year. So this is exactly what we have done in the solution. We have replaced the interest rate in the compounding factor with the effective interest rate. We have replaced the number of compounding period, the number of years with the number of compounding period. So the rest is just as before after doing this swap operations. All right, let's solve this problem. It says an engineering plans to borrow $3,000 from his company, credit union, to be repaid in 2 years at equal monthly installments. So the borrowed amount is $3,000, and the payment plan that the engineer is going to be subject to is a monthly payment plan that will continue for 2 years, which means for 24 months. For 24 months, the engineer is going to repay this debt with equal monthly installments, which means you will have a uniform series of payments. The credit union charges interest at an annual rate of 12%, but the interest compounds monthly on the unpaid balance. Now, in this sentence, it is stated that the credit union's nominal interest rate each year is 12%. However, the compounding occurs on monthly basis. Therefore, we need to determine the effective interest on a monthly base, compounding period, and which is very simple because the nominal interest rate is 12%, and there are 12 months in a year. The monthly compounding interest, or the effective interest per month per interest period, will be 12 divided by 12, which is 1%. So we know the payment plan will continue for 24 months, and in each month, the compounding will occur with a rate of 1%. How much money must the engineer repay each month? So we need to determine the installment size in this uniform series. Now, my principal is $3,000. Nominal interest rate is 12, and the number of compounding periods per year is also 12, and the number of years in this investment horizon is 2. Now, we are going to calculate the installment size A by multiplying the principal with uniform series capital recovery factor, right? So the uniform series capital recovery factor is actually formulated as I times 1 plus I to the power n divided by 1 plus I to the power n minus 1. However, in this case, we are going to replace the interest rate I with R over n. We are going to calculate the effective interest rate for each period. And in the investment horizon, we are going to use the number of compounding periods. So actually, this problem should be solved as if the annual interest rate is equal to 1% and there are 24 years to pay this debt. Okay? But you see, in reality, in this problem, the payment periods are on monthly basis. Therefore, we need to use the monthly effective interest rate, and the number of months will also be used in the formulation. Now, there are 24 months in this payment plan, and the effective interest rate is 0.01 as decimal. So when you multiply $3,000 with the uniform series capital recovery factor calculated under these changes, you will get the monthly payment amount of $141.22. Okay? Or you can directly use the compound interest table, and you can basically pull the capital recovery factor from there. All you need to do is to multiply the principal amount of $3,000 with a uniform series capital recovery factor, A over P, under 1% interest rate for each period and for 24 periods. So basically, you are changing the time unit of the problem. That's it. So in this problem, both the compounding and the payments are made on monthly basis. Therefore, the time unit is months. So you should determine your factor based on monthly units. And that capital recovery factor would be 0.04707 if you check the table. And again, you are going to get a value which is very close to the value you obtained in the exact formulation. Now, this is going to be your last question about the interest periods coinciding payment periods. Now, the next two problems are going to be much harder. So let's solve this for the final time, and we are going to focus on the other problems. An engineer wishes to purchase an $80,000 home by making a down payment of $20,000 and borrowing the remaining $60,000, which we will repay on a monthly basis over the next 30 years. Now, this is basically a mortgage investment, right? So the value of the house is $80,000. Now, there is a $20,000 of the engineer right now as a down payment, but the remaining 75% of the price of the house is going to be taken as a loan from a credit company or a bank. And on a monthly basis for 30 years, the engineer is going to repay that money. So how many months does it take to repay then? In 30 years, there are 360 months. Okay, almost for a lifetime. 30 years is almost for a lifetime. The engineer is going to repay some installment size in the end of each month for 30 years just to own the house. The bank charges interest at a rate of 9.5% per year. So the interest rate that the engineer is going to be exposed to is 9.5% per year. And this is the yearly interest rate, which means 9.5 is the nominal interest rate because the compounding occurs on monthly basis. So the engineer is going to repay the debt with monthly installments, and the compounding will also occur monthly. Therefore, in this problem, we can state again, the interest period is coinciding with the payment period. Okay, so the monthly compounding will occur. We need to determine the monthly effective interest rate, which is simple. You need to divide 9.5 to 12 to determine the monthly effective interest rate. And you also need to calculate how many months do we have in 30 years, which is 360 actually. So how much money must the engineer repay each month? This is the question. First of all, the principal is $60,000. Remember, it is not $80,000 because there's a down payment of $20,000. So the actual loan that is taken from the credit company or the bank is $60,000. And the nominal interest rate is 9.5%, and the number of months in a year is 12. And there are 30 years in total in the investment horizon. So what you need to do is you need to calculate the monthly installment size by multiplying the principal $60,000 with the uniform series capital recovery factor. But in the capital recovery factor, you are going to use the monthly effective interest rate R over M in place of the interest rate. And the number of payments in 30 years will be equal to 30 times 12, which is 360. Now, when you calculate this like that, the monthly payment size will be $504.51. This is going to be the monthly payment amount, 504.51. And the total amount of money that the engineer is going to pay in 30 years, because in each month the equal payment size is $504.51, it is going to be multiplied by 360. The total amount that the engineer is going to pay is $181,623 approximately, which is as 3 times large as the original loan. Okay, it is basically 3 times larger than the original loan, and this is how the mortgage payments work. Okay, so if you take a loan from the bank to purchase your house and you are being subject to a certain interest, nominal interest rate, this is how you calculate your monthly payment size. And of course, you need to be very careful at this point. This value should not exceed what you can afford, right? So depending on your monthly salary, you need to determine an annual monthly installment size, which will not exceed your affordable amount. All right, we are going to continue the next problem in the next video.